The dead stars that refuse to die. There is a kind of dead star that should not feel real. It is not a planet. It is not a normal star. It is not a black hole. It is something trapped between survival and total collapse. A corpse of a star so dense that a mountain could be compressed into the size of a cup. So violent that its magnetic field can tear atoms apart. And so strange that matter inside it may stop behaving like matter we understand. This object is called a neutron star, but that name is too calm. It sounds like a thing in a textbook, a small dot in an astronomy diagram. It is not calm. A neutron star is what remains when gravity nearly wins everything. Not completely. If gravity wins completely, the star becomes a black hole. But if something stops the collapse at the last possible moment, the universe produces one of its most extreme objects, a city-sized ball with the mass of a star. Imagine taking more mass than the sun, crushing it into a sphere only about the size of a city, then spinning it faster than a kitchen blender, heating its surface to millions of degrees, and giving it a magnetic field so powerful that ordinary chemistry becomes helpless near it. That is not science fiction. That is a neutron star. And to understand it, we must begin with a question most people do not ask. Why does a star exist at all? A star is not simply a ball of fire. Fire needs oxygen. A star is something deeper, a balance between two enemies. Gravity pulls inward. Fusion pushes outward. Every second, gravity tries to crush the star under its own weight. Every second, nuclear fusion in the core releases energy, and that energy pushes back. The star survives because these two forces negotiate with each other. Not peace, balance. Hydrogen fuses into helium. Energy escapes from the core. The outward pressure resists the inward fall. For millions or billions of years, the star holds itself together because gravity and fusion are locked in a struggle neither has yet won. But every star carries its death inside it. Fuel runs out. The question is, what kind of death the star has earned. A star like the sun will not become a neutron star. It is too small for that fate. It will swell, shed its outer layers, and leave behind a white dwarf, a dense remnant, but not a neutron star. For a much more massive star, the story becomes more violent. When hydrogen is exhausted, the core changes. The star burns heavier elements. Helium becomes carbon and oxygen. Carbon burns. Neon burns. Oxygen burns. Silicon burns. Each stage happens faster than the last, like a clock accelerating toward disaster. A massive star may spend millions of years burning hydrogen, then thousands or hundreds of years burning later fuels, then months, then days, and finally it reaches iron. This is where the universe becomes merciless. Iron is the ash at the end of the nuclear fire. Fusion normally gives energy back to the star. That energy is what holds gravity away. But iron does not give useful energy when fused in the same way. Iron is a dead end for the star's core. So when the core fills with iron, the engine fails. Gravity has been waiting the entire time. Now it moves. The core collapses. Not slowly, not politely. The inward fall becomes catastrophic. Electrons and protons are forced together under pressures beyond ordinary imagination. They combine into neutrons, releasing floods of neutrinos. Matter that once took up a volume larger than Earth is crushed into something only miles across. This is the first great mystery. What stops the collapse? Why does the star not always become a black hole? Because neutrons do not behave like ordinary dust that can simply be packed forever. At extreme density, quantum physics and the behavior of nuclear matter begin to resist. The collapse slams into a new kind of pressure, not the pressure of heat like in a normal star, but the pressure of matter forced into one of its most extreme possible states. The core becomes almost like one enormous atomic nucleus, not an atom, not a molecule, a star-sized remnant made of nuclear matter. The outer layers of the star are still falling inward. They crash into this newborn dense core. A shock wave forms. Neutrinos carry away enormous energy. The star tears itself apart in a supernova explosion, throwing its outer layers into space. For a brief time, one dying star can shine with the power of billions of stars. The outside is destruction. The inside is birth. What remains is a neutron star, a dead star that did not die all the way. Now ask the second mystery. How can something only the size of a city weigh more than the sun? The answer is that almost all ordinary emptiness has been removed. Atoms are mostly space. If you imagine an atom as a vast stadium, the nucleus is a tiny object at the center, and the electrons are spread through the empty region around it. Matter feels solid to us because of electromagnetic forces, not because atoms are full. But inside a neutron star, ordinary atomic structure has been crushed out of existence. Electrons and protons have been forced together. Nuclei are no longer sitting politely apart. Matter is squeezed to densities close to the density of atomic nuclei. This is why neutron star matter is so difficult for the human mind to hold. A teaspoon of it would weigh billions of tons. Not because it is magically heavy, because it contains an absurd amount of mass in an absurdly small volume. If you could take a tiny cube of neutron star material and place it on Earth, it would not behave like a normal object. Its gravity, pressure, and instability outside the neutron star environment would make the idea almost meaningless. But as an image, it tells you the truth. This matter is near the limit of what matter can be before becoming a black hole. And yet, a neutron star is not simply dense. It is also violently curved space-time. Its gravity is so strong that light leaving its surface is bent. In some cases, light from the far side can curve around toward us, allowing an observer to see more of the surface than should be possible on an ordinary sphere. Imagine looking at a ball and seeing part of its back, because gravity has bent the light around the object. That is the kind of world we are entering. A neutron star is not a place where common sense survives easily. The surface gravity would be crushing beyond imagination. A mountain on such a star could be only a few centimeters high and still contain enormous mass. The surface may be millions of degrees hot when the neutron star is young. The escape speed is a significant fraction of the speed of light. And if the neutron star gains too much mass, the balance fails. Gravity wins the final argument. The neutron star collapses into a black hole, so a neutron star lives on a knife edge. Below it, ordinary stars. Above it, black holes. It is the universe's last stand before darkness. But now comes the third mystery. What is inside it? From the outside, we can measure mass, radius, temperature, magnetic field, spin, and radiation. But the interior is a locked laboratory. We cannot build neutron star matter on Earth in stable amounts. We cannot drill into a neutron star. We cannot send a probe to survive its surface. So we use physics, we use mathematics, we use gravitational waves, we use X-rays, we use pulsars. We listen to the star by watching how it spins, how it cools, how it shakes, how it bends light, and how it behaves when it collides with another dead star. The outer layers may contain iron nuclei, the remains of the supernova squeezed into a rigid crust. Beneath that, as pressure increases, nuclei become more neutron-rich. Electrons are forced into protons. The deeper we go, the stranger matter becomes. Eventually, near the bottom of the crust, nuclei may be squeezed into bizarre shapes, not round atoms, not familiar crystals, long rods, flat sheets, twisted structures. Physicists call this nuclear pasta because even at the edge of the universe's most extreme matter, human beings still name things after food. Spaghetti, lasagna. Layers and strands of nuclear matter, possibly among the strongest materials in the universe. But below that crust, in the core, certainty weakens. Maybe the core is mostly neutrons in exotic states. Maybe protons become superconducting. Maybe neutrons become superfluid, flowing with almost no resistance. Maybe deeper still, neutrons themselves break into quarks. Maybe strange quarks appear. Maybe there is a form of matter so alien that the periodic table is no longer the right language. This is why neutron stars are not just objects. They are experiments made by gravity. Every neutron star is a laboratory larger than a city and denser than anything we can create on Earth. The universe built the machine. We are trying to read the results from light years away. And now comes the fourth mystery. Why do some neutron stars pulse like cosmic lighthouses? Because the star is not only dense, it is spinning. When a massive star collapses, it shrinks enormously. And when a spinning object becomes smaller, it spins faster. You have seen this with a skater on ice. When the arms are stretched outward, the spin is slower. When the arms are pulled inward, the spin becomes faster. Now imagine this happening to a star. A star larger than the sun collapses into something only miles wide. Its rotation is concentrated into a tiny remnant. What was once slow becomes violent. The neutron star may spin many times per second. Some spin hundreds of times per second. A dead star becomes a cosmic engine, but rotation alone is not enough. The neutron star also carries a powerful magnetic field. During collapse, the magnetic field is compressed and intensified. Field lines that once stretched through a massive star are squeezed into a city-sized object. The result can be astonishing. A magnetic field millions, billions, even trillions of times stronger than anything familiar on Earth. Charged particles move along those magnetic fields. Radiation is fired outward in beams, but the magnetic poles are not always perfectly aligned with the spin axis. So as the neutron star rotates, the beams sweep through space. If one of those beams crosses Earth, we see a pulse, flash, silence, flash, silence. Not because the star is turning on and off, but because its beam is sweeping past us again and again. That is a pulsar, a lighthouse built from a dead star. The regularity can be extraordinary. Some pulsars keep time better than many human-made clocks. They are so precise that astronomers can use them to test gravity, study space, and search for tiny disturbances in space-time. That is what I love about them. A dead star becomes a clock. A corpse becomes an instrument. The universe takes the collapsed heart of a massive star and turns it into a rhythm. But now comes the fifth mystery. What happens when the magnetic field becomes even stronger? Then we meet the magnetar. A magnetar is a neutron star whose magnetic field is so extreme that it becomes the main character of the story. Its magnetic energy can twist the crust, stress the star, and release enormous bursts of high-energy radiation. On Earth, magnetic fields are useful. They guide compasses. They help motors work. They shape auroras when particles from the sun meet Earth's magnetic shield. Near a magnetar, the magnetic field becomes violence. Atoms could be distorted. Chemistry would not behave normally. A flare from a magnetar can release more energy in a fraction of a second than the sun releases over vast stretches of time. These objects remind us that a neutron star is not merely heavy. It is extreme in every language physics has. Gravity, density, temperature, rotation, magnetism. A neutron star is what happens when nature takes many kinds of extremity and puts them into one object. And still, the story is not finished, because the most powerful moments come when neutron stars are not alone. Now comes the sixth mystery. What happens when two neutron stars find each other? They may orbit for millions of years. Two dead stars locked together, slowly losing energy as gravitational waves ripple away into space-time. Their orbit shrinks, they circle faster, the rhythm becomes more urgent. Then, in the final moments, they race around each other at terrifying speeds. Space-time itself trembles, the stars collide. For a brief moment, the universe creates one of its most violent laboratories. Neutron-rich matter is thrown into space. The collision may form a heavier neutron star or collapse into a black hole. Jets can launch, light can erupt, gravitational waves spread outward at the speed of light. This explosion is called a kilonova, and it carries one of the most beautiful answers in astronomy. Where does gold come from? Not all of it, perhaps, from one kind of event. The full cosmic story is complicated, but neutron-star mergers are one of the great factories of heavy elements. In the debris of these collisions, atomic nuclei can rapidly capture neutrons, building elements far heavier than iron: gold, platinum, uranium, elements too heavy to be made easily in the normal burning heart of a star. So when you hold gold in your hand, you may be holding the memory of dead stars colliding, not metaphorically, physically. The atoms in that metal may have been born in an event so violent that it shook space-time itself. That is the strange poetry of the universe. Beauty is often the ash of catastrophe, a ring on a finger, a circuit inside a machine, a precious metal buried in Earth's crust. All of it may carry the signature of neutron stars that died together long before the sun existed. Now return to the beginning. A neutron star is born when a massive star dies. But sometimes neutron stars must die again to create what the next generation needs. The first death makes the neutron star. The second death, in a merger, can help make the heavy elements. Stars die to enrich the universe. Neutron stars collide to finish the periodic table. Then those elements drift through space. They mix with gas. They become part of new clouds. Gravity gathers the clouds into new stars, new planets, new oceans, new chemistry. Eventually, some of those atoms become part of us. This is not only astronomy, this is ancestry. The calcium in your bones, the iron in your blood, the gold in human treasure, the uranium buried in rock. These are not separate from the stars. They are chapters of the same story. A neutron star may seem distant, cold, and impossible, but its history is inside the modern world, inside technology, inside Earth, inside the elements that make life possible. That is why neutron stars matter. They are not only dead stars. They are bridges between destruction and creation. Now ask the final mystery. Why does the universe make such extreme things? Perhaps because the universe does not think in terms of comfort. It thinks in terms of law. Gravity does not stop because matter becomes frightened. Quantum pressure does not appear because the universe is kind. Nuclear matter does not resist collapse because it has purpose. Everything happens because the laws allow it. And when the laws are pushed to their edge, the universe produces objects that feel impossible. A black hole is one edge. A neutron star is another. The neutron star is especially fascinating because it stands just before the final darkness. It is not ordinary matter anymore, but it has not yet vanished behind an event horizon. It is visible, it pulses, it cools, it shakes, it merges, it announces itself with beams and waves and explosions. It lets us study the almost impossible. It is a message from the borderland between stars and black holes. A white dwarf says, matter can resist gravity. A black hole says, gravity can win completely. A neutron star says, not yet. That is its entire character. Not yet, not a normal star, not a black hole, a final resistance. A city-sized remnant holding more mass than the sun, spinning in the dark, bending light around itself, carrying a magnetic field that can scar space with radiation, and hiding inside it forms of matter we may not yet have names for. You could call it dead. But dead things do not usually keep time for the galaxy. Dead things do not usually forge gold in their collisions. Dead things do not usually teach us what matter becomes when gravity is almost absolute. So perhaps a neutron star is not simply the corpse of a star. Perhaps it is the universe's way of showing us what remains when everything unnecessary has been crushed away. No atmosphere like Earth, no burning surface like the sun, no gentle chemistry, only mass, spin, Gravity, magnetism, nuclear matter, and time. A star once lived there. It burned hydrogen. It made light. It fought gravity for millions of years. Then its fuel ended, its core collapsed, and in one final act of violence, it threw its outer body into space. But the heart remained, compressed, spinning, unthinkably dense. A warning that matter has deeper forms than the ones we touch. A reminder that death in the universe is rarely only an ending. Sometimes death becomes a clock. Sometimes death becomes a lighthouse. Sometimes death becomes gold. And sometimes, in a patch of space only the size of a city, the universe hides one of its greatest questions. What is matter when gravity has taken almost everything else away? That is the terrifying beauty of neutron stars. They are small enough to fit between human cities, massive enough to bend light, dense enough to shame imagination, and mysterious enough to remind us that the universe is not finished teaching us what reality can be. What feels more impossible to you, that a dead star can become a city-sized atomic nucleus, or that the gold on Earth may have been born when two of those dead stars destroyed each other? Subscribe to explore more mysteries through the questions that still lead humanity to the edge of reality.